Let's talk about integrated rate laws, okay? So we already know about rate laws. Out here, integrated means we're using integration, which is a calculus, a method in calculus, integration in calculus, to change the form of the rate law into something more manageable, something that we can kind of use more efficiently. Now, don't be worried by calculus. If you don't know calculus, or if you are unfamiliar with calculus, or you've forgotten calculus, you learned it sometime, you forgot it, we're not going to worry about deriving it using calculus. We're just going to show you how to get to the point where you use calculus, and then we'll show you the solution after we use calculus, and then how to use the solution. Okay, so there are two ways we have learned so far how to write out the rate of a reaction. So let's take, for example, let's back up a bit. Let's take, for example, a very simple reaction. A goes to products. One way to write the rate is the change in A over the change in time. So change in A over the change in time, and because A is a reactant, there has to be a negative to the left of it. Okay, another way to write the rate is in the form of a rate law. So the rate would be equal to a constant K times the concentration of A raised to the order of the reaction, which is X. Okay, now the way to use an integrated rate law, since these two rates are just two different ways to express the rate of the same reaction, we can make these two equal to each other. So just draw a straight line out here. So we can write negative delta A over delta T is equal to K times A raised to the power X. At this point in time, we'll use calculus integration to find the integrated rate law. And there are three specific scenarios we'll look at where X is equal to 0, which would be the case of a zero order reaction. X is equal to 1, which would be the case of a first order reaction, and X is equal to 2, which would be the case of a second order reaction. Okay, so for zero order reaction, we can just change this little X to 0. Okay, and what we're doing is, when we use the integration, we're integrating between limits. Okay, so the limits out here, again, don't worry too much about calculus. I'm just trying to define the boundary conditions. The limits out here is when t is equal to 0 seconds, so that means at the start of the reaction, and then when t is equal to t seconds, which is when the reaction, which is the stopping point. Okay, so the interval of time we're looking at. And then the other limit is the concentration of A. So we're going to say the concentration of A, which is A naught, that is at time 0. So when the reaction begins, that's the concentration of A naught. And then when the time stops, so at t seconds, the concentration of A is, let's call that just A. Okay, so now we'll just put that, if we put those boundary conditions into this and integrate it, we will get the solution would be A naught minus A is equal to KT. Okay, now if we rearrange this, okay, and we take the A naught and we put it that side, we get minus A is equal to KT minus A naught. And let's go ahead and get rid of the negative sign, so flip the sign of everything. That would give us A is equal to minus KT plus A naught. And now we actually have something that kind of looks like the equation of a straight line. I'll compare it out here. we have the equation of a straight line is y is equal to mx plus b, okay? B is the y-intercept, so that's equal to the a naught. M out here is equal to the negative k, okay? Negative k. T is the same as the x, and y is the same as the a, okay? So that means if we plot this, we can actually end up with a straight line, okay? So let's go ahead and do it. Okay, so we have a plot out here. We have the y-axis, the x-axis. We put the x, which is the t, out here. We have the a, which is the y in this case, okay? And we have a negative k. Negative k means the slope needs to go down this way, okay? So therefore, if you plot this, it will look something like this, where the slope of this line is equal to negative k, okay? So now what's the value of all this? The value of this is, if you have a reaction, okay, if the reaction is given to you where different concentrations are given to you at different points in time, you can plot the concentrations versus the time, and that will give you the slope. And from that slope, you can plug it into this equation out here to find whatever parameter you're looking for. For example, if you're looking for the rate constant, you would find the rate constant, okay? Let's direct our attention to the case of a first order reaction. In the case of a first order reaction, it would be minus delta A over delta T is equal to K times A raised to the power 1, because it's a first order reaction. And now if we integrate, again, the limits out here are T goes from 0 seconds, okay, that's at the beginning, to t seconds. So I'll just write 0 seconds to t seconds, and then the concentration of A at 0 seconds is A naught, concentration of A at t seconds is A, okay? So if we integrate between those limits, we would get the expression ln of A over A naught is equal to minus kt, okay? Now what we can do is, we can rearrange this expression, because if you recall from your previous math classes, log of A over B is equal to ln of A minus ln of B, okay? So we'll apply that out here. So we get ln of A minus ln of A naught is equal to minus kt. Let's rearrange this. So let's take the A naught and put it this side. So we get ln of A is equal to minus kt plus ln of A naught. And the reason we rearrange this is because we wanted to mimic the equation of a straight line. So that's the y, and then we have the mx, so the t is the x, the negative k is the m, and that's the b. So now if you plot this, we have the vertical and the horizontal axis. You have the t out here. You have not a, but ln of a is on the horizontal axis, the vertical axis. Then the slope is a negative k, right? So there you have it. That's the negative k, the slope of that straight line. So that's kind of the plot you'd get. It'd be a straight line. It'll have a negative slope. And notice carefully the y-intercept. So wherever this hits the vertical axis, that distance is going to be ln of A naught. So again, when you plot this, if you're given a certain number of conditions where you have changing times and changing concentrations, you can plot that. You can plot the log of the natural log of the changing concentrations with the time, and you would get a straight line, and from that straight line you could find out the rate constant, okay, and some other values if you some other parameters if you're interested. So now let's take a look at a second order, the case of a second order reaction. So in the case of a second order reaction, let's write that down, second order, we have minus change in the concentration of A over change in time is equal to K times a raised to 2 because it's second order, okay? And again, if we integrate between the same intervals that we've been doing for the zeroth and the first order, we'd get 1 over a minus 1 over a naught is equal to kt. Let's rearrange to mimic the form of a straight line. So we'd get 1, remember, the a term is always the y, and then we take this, that becomes the y-intercept, so we put that on the other side, so that becomes kt plus 1 over a naught, okay? And then if we plot this, that's the t, this is the 1 over a, and then notice carefully it has a positive slope, okay? So that graph will look something like that. The slope of this line is equal to k, and that is the y-intercept, which is 1 over a naught, okay? So to summarize, if we kind of had to summarize the integrated forms for 0, first and second order, these would be the equations. I highly recommend writing this down on a piece of paper and keeping it handy because you'll need this to solve problems. So for the zeroth order, you'd have a is equal to minus kt plus a naught. For the first order, you'd have ln of concentration of a is equal to minus kt plus ln of concentration of a naught. And for the second order, you have 1 over a is equal to kt plus 1 over a naught. Now what we can do is we can extrapolate from this the concept of half-lives. So what exactly is a half-life? Half-life is simply the time it takes for a reactant to reach half its initial concentration, okay? So I'll just write that down here. Time taken to reach half the initial concentration, which means for each of these we can derive the half-life. All we have to do is plug in for a out here, we write a naught over 2, okay? So I'll just do that in a different color out here for the first one, for these. So for the zeroth order, that becomes a naught over 2 is equal to minus kt plus a naught, and then we just combine them. So if I bring this a naught over to the left to combine the a naught terms, I get a naught over 2 minus a naught is equal to minus kt. That becomes minus a naught over 2 is equal to minus kt. And now notice carefully, since it's half-life, we want to call the t, we want to put a little 1 over 2 to the right of the t as a subscript, okay, because we're saying that that t, that time, is the time taken to reach half the initial concentration. Now we cancel out the negative signs and we pull the k over to this side, so we get t half for this is equal to a naught over 2k. Okay, so that is the half-life for a zeroth order reaction. Okay, so we'll go ahead and create another column out here and call that, call that half-life. So T half for the zeroth order reaction is going to be a naught over 2k. Now you can follow the same logic to derive the half-life for each of these. I'm just going to go ahead and write them down, and I'll leave that for you to do as your homework to figure out each of these. So the half-life for the first order is ln of 2 over k. Okay, and that ln of 2 actually simplifies to 0.693 over k. Okay, and then the half-life for the second order is 1 over a naught k. Okay, so there you have the expressions for the half-life. Now here's the interesting thing. If you're really once you get really comfortable with these, you don't even have to remember these half-lives. You can if you want to, but you can always derive the half-life from the integrated forms if you know what the meaning of half-life is. Okay. Alright, so the last thing we're going to do in this video is we're going to talk about the units of K, okay? And why we are talking about the units of K is, number one, you can derive it, but oftentimes you'll see in problems the unit of K is given and the question would be asked to you, what's the order of the reaction? So if you know the units of the K, you can figure out the order of the reaction. The unit of K for a zero order reaction is molar per second. The unit of K for a first order reaction is only per second. There's no concentration term in it. And the unit of K for a second order reaction is actually per molar per second. These could be simplified. You may not be very familiar with the capital M used for molar. So if you recall that M, molar, is equal to moles per liter, then this could be simplified to moles per liter per second. Okay. This of course doesn't have concentration, so we keep that as is, and this could be simplified as per molar. Now because liters at the bottom out there, that becomes liters and per second. There you have it. Now if this becomes too complicated, just keep it simple like this. Change anything that's moles per liter into M, a capital M, and you're good to go. Okay, I hope that made sense. Thank you for watching.